The 17th century was an age of restless curiosity. Across Europe, telescopes had begun to peer into the heavens, and new instruments were measuring time, angles, and motion with precision no generation had known before. The old world of divine causes and invisible spirits was slowly giving way to one ruled by mathematics and observation. In this age, a quiet young scholar from rural England would redefine the very language of nature. His name was Isaac Newton, and his work would change forever the way humanity understood the sky above and the ground beneath its feet. In his youth, Newton studied at Cambridge, surrounded by the legacy of Galileo and Kepler. He absorbed their discoveries, their insistence that the universe followed lawful order. Yet something about those laws remained unfinished. Kepler had shown that planets traced elliptical paths around the sun, but he could not say why. Galileo had studied falling bodies and the speed of projectiles, but the reason objects accelerated toward the Earth was still a mystery. Newton wanted not only to describe what happened, but to understand the invisible rule behind it. During the Great Plague of 1665, when Cambridge closed its doors, Newton returned to his family farm in Woolsthorpe. There, in isolation, he began to think about motion, force, and the hidden harmony connecting the apple that falls and the moon that circles the Earth. The story of the apple, though told in many versions, captures something true about his thought. He asked a simple question: if the apple falls to the ground because the Earth pulls it, could the same pull extend all the way to the moon? He began to see the universe as one great machine of predictable movement. Through careful reasoning and mathematics, he derived his law of universal gravitation. Every piece of matter, he realized, attracts every other piece of matter with a strength that depends on two things: their masses and the distance between them. The greater the mass, the stronger the attraction. The farther apart they are, the weaker it becomes, falling off as the square of the distance. Though Newton did not use modern symbols, his equation can be read today as the gravitational force equals the product of the two masses multiplied by a constant, divided by the square of the distance between them. This was a breathtaking step. For the first time, the same rule explained both the fall of an apple and the orbit of the moon. What had once been separate realms, earthly motion and celestial motion, were united under one mathematical principle. The heavens were no longer governed by divine perfection, while the earth followed its own rules. They were both part of a single fabric of cause and effect. Newton's insight erased the boundary between the sky and the ground. Yet Newton was no mystic. He avoided claiming that he knew how this attraction worked. In his famous words, "I frame no hypotheses." He could calculate the strength of gravity and predict motion with astonishing accuracy, but the mechanism behind the attraction remained unknown. How could one object influence another across empty space without any physical link or contact? This question would trouble scientists for centuries. Despite the mystery, Newton's achievement was absolute. When he published his Philosophiae Naturalis Principia Mathematica in 1687, it became the foundation of modern physics. The Principia provided not only the law of gravitation, but also the laws of motion, clear mathematical statements that could describe everything from a falling stone to a swinging pendulum, from the tides to the paths of planets. The world was reborn as a clockwork universe, perfectly ordered, running by rules that could be written and solved by human minds. The influence was immediate and immense. Observatories used Newton's equations to predict eclipses and planetary alignments with unprecedented precision. Engineers used his laws to design bridges, cannons, and clocks. Philosophers saw in his system the triumph of reason over mysticism. The cosmos seemed no longer a place of divine intervention, but a vast mechanism governed by universal order. And yet, behind that certainty, a faint unease remained. If gravity acted instantly at any distance, did that not imply some hidden connection faster than light itself? How could force leap through the void, touching one mass with the presence of another far away? Newton himself admitted that such action at a distance was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Still, he left the question unresolved. For 2 centuries, the world would live comfortably within Newton's clockwork, even as small cracks began to show at its edges. The equations worked, but their deeper meaning awaited a new mind to challenge the very notion of force itself. For generations after Newton, the Principia became the sacred text of natural philosophy. Every student of science learned to see the universe as he described it, a realm of matter, motion, and forces acting across space. From the movement of cannonballs to the dance of planets, all could be predicted once the forces were known. The concept was powerful in its simplicity. To know the world, one needed only to measure mass, distance, and time, and then let Newton's equations do the rest. In that vision, space and time themselves were merely the stage upon which events occurred. They were absolute and unchanging, silent containers that held everything else. A rock, a planet, a star, all moved within this vast emptiness, each motion determined by forces acting from afar. For most of the 18th and 19th centuries, this picture seemed complete. Astronomers used Newton's formulas to chart planetary orbits with such precision that they discovered entire worlds before they were seen. When Uranus deviated slightly from its predicted path, mathematicians calculated where an unseen planet must be tugging on it. Telescopes turned to that point, and Neptune was found. It seemed that Newton's mathematics could see the invisible. This success was not only scientific but philosophical. It shaped how people thought about nature itself. The universe became a grand machine built by divine order, but running perfectly well without divine interference. Every event had a cause, every motion a reason. If one could know all forces and all positions at a single moment, one could, in theory, predict the entire future of the cosmos. This belief in determinism was one of Newton's lasting legacies. The world was logical, measurable, and obeyed timeless laws. Still, within that triumph lay its silence about why gravity worked at all. Newton had unified the heavens and the earth, but he had not explained the thread that tied them together. His gravitational constant described the strength of attraction, but it said nothing about the mechanism. What filled the empty space between two bodies? What carried the force from one to the other? For a while, scientists proposed that an invisible substance, a kind of universal medium called the ether, might fill the cosmos. Through this ether, perhaps, gravitational influence could travel. But even this idea was more hope than evidence. In the centuries that followed, Newton's laws were tested in every possible way, and they passed each trial with elegant precision. Pendulums swung, planets orbited, comets returned as predicted, and tides rose and fell on schedule. The mathematics never faltered. Yet as measurements grew more precise and instruments more sensitive, faint discrepancies began to whisper that not everything fit perfectly within Newton's clockwork. The orbit of Mercury, the smallest of the planets, shifted slightly in a way that calculations could not fully explain. The difference was tiny, a few arcseconds per century, but it refused to go away. For the physicists of the 19th century, such deviations were not only puzzles, but invitations. They believed that the cause must be hidden somewhere in the details, perhaps another unseen planet, perhaps some subtle imperfection in observation. It was unthinkable that Newton's laws themselves might fail. His system had explained too much, too well. To doubt it was to question the very logic of nature. And yet, beneath the growing towers of precision, another revolution was forming quietly. The discoveries of electricity and magnetism were revealing that the universe might not be a collection of isolated objects acting through empty space, but rather an interconnected field of influence. James Clerk Maxwell's equations showed that light itself was an electromagnetic wave moving through space, and that its speed was constant, independent of the motion of its source. This simple fact confirmed by experiment, would one day strike at the heart of Newton's conception of absolute space and time. For now, though, Newton's vision still reigned supreme. In the light of candle and telescope, the world seemed orderly, measurable, and complete. The clockwork ticked with infinite precision, and humanity believed it understood the machinery of creation. But time itself was preparing a correction, a quiet realization that the universe was not a stage, but a participant, not a fixed arena, but a living geometry still waiting to be discovered. By the dawn of the 19th century, Newton's ideas had become not just a scientific framework, but a philosophy of certainty. Every student, engineer, and astronomer worked under the same assumption: that gravity was an invisible force acting instantaneously between masses, that space was a silent emptiness, and that time flowed identically everywhere. It was a worldview so effective that it felt absolute. Ships navigated across oceans using Newton's tables, and cannon fire was guided by the same equations that described planetary motion. The reach of his laws stretched from human battlefields to the outer planets. But deep inside this triumph hid a paradox Newton himself had never resolved. In his letters, he confessed his discomfort with the idea of one body reaching across the void to pull on another without anything in between. It was a mystery he could not explain. He had the mathematics, but not the mechanism. That gravity should be innate, inherent, and essential to matter, he once wrote, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has a competent faculty of thinking can ever fall into it. And yet the theory worked so perfectly that no one dared change it. For 2 centuries, gravity remained an unquestioned law. The apple fell, the planets moved, the tides obeyed. Observations matched calculations so precisely that even its mysteries were forgotten. But the human spirit is restless, and as instruments grew more precise, the universe began whispering its contradictions. Tiny irregularities in the orbit of Mercury persisted, even after every known planet was accounted for. Light, once thought to require a medium to travel through, refused to behave like a vibration in any known substance. When physicists tried to detect the ether that was supposed to fill space, they found nothing. The Michelson-Morley experiment, performed in the 1880s, measured the speed of light in every direction and discovered it was always the same, no matter how the Earth moved. This was not possible within the Newtonian picture of motion. Nature was quietly breaking its old clock. The cracks were small but undeniable. Scientists such as Hendrik Lorentz, Henri Poincaré, and Ernst Mach began to suspect that the problem might not lie in matter or motion, but in the very concepts of space and time themselves. The universe, it seemed, was not content to be a static machine. It was hinting at something deeper, a geometry hidden beneath the apparent forces. Looking back, it is astonishing how close Newton had come to the edge of this revelation. His equations connected every object in existence, yet he left untouched the idea of what space and time truly were. He treated them as the unchanging background upon which nature acted. But what if that background was not fixed? What if space and time could themselves bend, stretch, and respond to the presence of matter? Such questions were impossible to imagine in Newton's century, but they would soon become the very language of physics. The seeds of change were already planted. In a world that believed the cosmos ran like a perfect clock, one young man would arrive with a new way of seeing, a vision where gravity was no longer a mysterious pull through emptiness, but a natural consequence of how space and time themselves behaved. His name was Albert Einstein, and his revolution would not destroy Newton's universe, but reveal its deeper truth. As the 19th century gave way to the 20th, humanity stood unknowingly at the threshold of a transformation. The old force that ruled the heavens would soon vanish into geometry, and the familiar idea of gravity would dissolve into the curvature of spacetime. The clockwork universe was about to awaken. By the middle of the 19th century, the universe appeared solved. Newton's equations had survived every test, and their predictions were woven into the very fabric of daily life. Ships navigated by celestial mechanics, observatories traced the orbits of planets with clock-like regularity, and engineers built the machinery of an industrial world under the same rules that governed the heavens. It was an age of confidence, a time when science promised certainty. To many, the cosmos seemed an enormous mechanism running flawlessly under the steady hand of mathematics. Yet beneath that certainty, small disturbances began to surface, faint imperfections that refused to vanish no matter how carefully they were measured. The first and most famous came from the planet Mercury. For 2 centuries, astronomers had charted its motion around the Sun, comparing observation with Newton's predictions. Most planets fit perfectly, but Mercury's path showed a subtle difference. Each time it completed an orbit, the point where it came closest to the Sun, its perihelion, advanced slightly more than Newton's laws allowed. The difference was tiny, only a few dozen arcseconds over a century, but no amount of correction could make it disappear. At first, scientists assumed another planet must be disturbing Mercury's orbit. They called it Vulcan, a hypothetical world hidden near the Sun, too bright to see in ordinary telescopes. For decades they searched, scanning the solar glare for the phantom planet that would rescue Newton's perfection. It was never found. The problem of Mercury was not alone. As instruments became more sensitive, light itself began to challenge the foundations of classical physics. For centuries, thinkers had debated whether light was made of particles or waves. Newton believed it was corpuscular, a stream of tiny objects moving through space, while later experiments showed it could interfere and diffract like a wave. But waves, as everyone knew, needed something to travel through: water, air, or some medium capable of vibration. Since light crossed the emptiness between stars, physicists imagined that all of space must be filled with an invisible substance, a cosmic ocean they called the luminiferous ether. For a time, the ether solved everything. It gave a physical meaning to empty space and provided a carrier for light's motion. But then came the experiment that shattered that illusion. In 1887, Albert Michelson and Edward Morley set up an intricate device that split a beam of light and measured its speed in perpendicular directions as the Earth moved through the ether. If the planet were truly sailing through such a medium, then light should move slightly faster in one direction than another. Yet every attempt showed the same result. Light's speed never changed. The ether, if it existed, was undetectable. This failure was devastating. It struck at the heart of Newton's framework, for if there was no ether, then what filled space? How could forces act across nothing? And if light's speed was always the same, no matter how one moved, then something was wrong with the very notion of motion itself. While physicists wrestled with these contradictions, another revolution was unfolding in the realm of electricity and magnetism. James Clerk Maxwell, a Scottish physicist of rare insight, had written 4 equations that unified these two forces into one theory of electromagnetism. From them emerged a surprising conclusion that light was an electromagnetic wave, and its speed could be derived directly from the constants of electric and magnetic interaction. When the numbers were calculated, they matched the measured speed of light exactly. Suddenly, light was no longer mysterious. It was a natural vibration of the electromagnetic field. But this discovery carried an unsettling implication. If light speed was fixed by the properties of space itself, and if it was the same for all observers, then the old ideas of absolute space and absolute time could not both survive. Something deeper would have to give. For the moment, however, the scientific world tried to preserve the old structure. Elaborate mathematical tricks were invented to explain away the stubborn constancy of light. Physicists like Hendrik Lorentz proposed that moving objects might shrink slightly in the direction of motion, compensating for the missing ether wind. The equations worked, but they felt artificial. as though nature were being forced to obey human expectation rather than its own truth. The age of perfect certainty was beginning to tremble. The cracks in the clockwork grew wider with every experiment, every unexplained deviation. Behind the comforting image of a predictable universe, a deeper mystery was preparing to emerge. A mystery that would demand a complete reimagining of space, time, and the very meaning of gravity itself. As the 19th century advanced, the idea of a perfectly predictable universe began to lose its shine. What once seemed unbreakable now revealed faint distortions, like hairline cracks in glass. Mercury's wandering orbit, the elusive ether, and the strange behavior of light whispered that something fundamental was wrong, not with our measurements, but with our assumptions. The pillars of Newton's world were trembling. To many physicists, this was deeply unsettling. Newton's laws had built an empire of understanding. They had guided ships across oceans and predicted the return of comets with uncanny precision. Every discovery since had seemed to confirm that nature followed strict mathematical laws. The world had grown accustomed to the comfort of certainty. But now, in laboratories and observatories across Europe, the data refused to fit the mold. James Clerk Maxwell's electromagnetic theory, elegant and complete, introduced a new way to think about forces. Instead of instantaneous actions between distant objects, he spoke of fields, invisible structures filling space, capable of storing and transmitting energy. The concept was revolutionary. A field was not a thing in the traditional sense. It was a state of space itself, a description of how energy and influence existed even in the absence of matter. This was the first step toward abandoning the notion that space was merely empty. Still, the idea of a field did not sit easily beside Newton's gravity. Newtonian gravity acted instantly, while Maxwell's fields rippled at a finite speed. In Maxwell's world, nothing could transmit information faster than the speed of light. But if gravity were instantaneous, as Newton's equations implied, then it seemed to belong to an entirely different order of nature. The contradiction was subtle, yet profound. Physicists sought ways to reconcile the two visions. Some proposed that gravity too might be a kind of field, though no one could yet describe how. Others tried to preserve the ether by reshaping it into new mathematical forms. The more they tried to mend the cracks, the more the structure resisted repair. The ether had once seemed a natural necessity. How else could light waves exist? But experiment after experiment returned the same answer. The ether left no trace. It did not slow light, did not push or pull, did not affect the motion of planets or the passage of time. It was an invisible stage that produced no evidence of its own existence. Meanwhile, technology pushed the boundaries of observation. Spectroscopes split starlight into colors, revealing the fingerprints of elements burning in distant suns. The precision of measurement increased beyond what Newton could have imagined. And with that precision came new questions. If light was a wave, and its speed unchanging, what did that say about time itself? Could clocks moving through space disagree about how fast time passed? Such thoughts were radical, almost unthinkable, and yet the mathematics was leading in that direction. In Vienna, the philosopher Ernst Mach challenged the very idea of absolute space. He argued that motion had meaning only in relation to other objects, not against some unseen backdrop. If all matter vanished, he asked, what would it even mean to say that something was moving? His challenge struck at Newton's deepest assumption, the idea that space and time existed independently of matter. Mach's criticism would later echo in the mind of a young patent clerk who would change the course of physics forever. The scientific world stood at a crossroads. On one side lay the old certainty of Newton, with its clear forces and absolute geometry. On the other stood a growing awareness that space and time might not be as rigid as they seemed. The evidence was fragmentary, the implications uncertain, but the unease was spreading. nature was whispering a new language, one no one yet understood. The great machine of the cosmos had begun to hum in unfamiliar tones, and somewhere, in the stillness of early 20th century Europe, a quiet thinker was listening. The turn of the 20th century marked the twilight of the classical age. Scientists had measured almost everything that could be measured, from the motion of planets to the speed of light. They believed they stood on the verge of total knowledge, with only a few small puzzles left to solve. But those small puzzles were not cracks to be patched. They were openings to a new reality. The mystery of Mercury's orbit, the vanishing ether, the stubborn constancy of light, each was a whisper from nature, calling for a deeper truth. Among the thinkers confronting this confusion was a generation raised entirely under Newton's shadow. They had inherited a cosmos ruled by absolute time, infinite space, and forces acting through the void. But as they compared theory to experiment, they found that the universe refused to behave according to those absolutes. When Michelson and Morley failed to detect the ether, they did not just disprove a substance, they questioned the very foundation of motion itself. If there was no ether, no universal frame to measure against, then what did it mean for something to be at rest or in motion? The question was both philosophical and physical, and it could no longer be ignored. Lorentz tried to save the old picture by suggesting that objects physically contracted in the direction of their motion. Henri Poincaré refined the mathematics, pointing out that time itself might depend on the observer's motion, though he still believed in an underlying ether. These were brilliant attempts to preserve Newton's legacy, but they carried the scent of desperation, ingenious patches on a theory whose foundation was quietly shifting. At the same time, the nature of energy itself was being re-examined. Experiments with black-body radiation and the photoelectric effect hinted that light behaved both like a wave and like discrete packets of energy, later called quanta. The universe was beginning to reveal that it was not the continuous, clockwork mechanism people once believed, but a dynamic interplay of energy and geometry. In this atmosphere of uncertainty, a young man named Albert Einstein worked as a patent clerk in Bern, spending his quiet hours thinking about the contradictions between electromagnetism and mechanics. He wondered what it would be like to ride alongside a beam of light. If one could travel at the same speed as light, would the wave appear frozen in space? According to Maxwell's equations, this could never happen. Light's speed was the same for every observer, no matter how fast they moved. To accept this meant that space and time could no longer be absolute. Einstein's insight would come soon, but in this moment, the final years before 1905, physics stood on the brink of transformation. The clockwork universe, once perfect and eternal, was now trembling with uncertainty. The smallest details, once ignored, were revealing enormous consequences. It was becoming clear that the old force of gravity, the invisible pull through empty space, could not remain untouched by the changes sweeping through physics. Even Newton, if he could have seen this era, might have understood. He had built a world of equations that reached to the stars, yet he had left room for mystery. He never claimed to know the true nature of gravity, only how it acted. Now, that humility would prove prophetic. The time had come for someone to ask not how gravity pulled, but what gravity truly was. And so, into this world of contradiction and curiosity, Albert Einstein would step forward. With patience, logic, and imagination, he would dissolve the last remnants of absolute space and time, revealing that gravity was not a force acting through the void. It was the very shape of the void itself. The 20th century began with an illusion of completion. The textbooks were filled with equations that seemed to describe everything. Students were told that only a few minor details remained to be explained, that physics was nearly finished. Yet beneath this calm certainty, a quiet storm was gathering in the mind of a young man who did not belong to any university, who had no laboratory, and whose desk was piled not with instruments, but with patent applications. His name was Albert Einstein, and he was about to rewrite the very fabric of reality. Einstein was born in Ulm, Germany, in 1879 and grew up fascinated by the mystery of light. As a child, he remembered holding a compass and wondering how the needle could move, guided by something invisible. That curiosity stayed with him. By the time he reached adulthood, science had defined the motion of planets, the behavior of gases, and the laws of energy. Yet no one could explain what light truly was. Was it a wave traveling through some invisible ether? Or was it something even more profound? Working long hours at the Swiss Patent Office in Bern, Einstein had little more than his imagination and his mathematical insight, but he used them with unmatched precision. He began by asking simple questions that others ignored. What would the world look like if you moved alongside a beam of light? If you could catch up with it, would you see the wave standing still? Maxwell's equations, which governed light, said such a frozen wave could not exist. The only conclusion, unthinkable to most physicists of his time, was that no matter how fast one moved, light's speed would always remain the same. This single realization broke the foundation of Newton's absolute space and time. If the speed of light was fixed for everyone, then the concepts of now, before, and after could no longer be universal. Time itself must depend on motion. Two observers moving differently could measure time in two different ways, and both be correct. Space and time, long considered separate and absolute, were in fact intertwined. Einstein's paper on special relativity, published in 1905, showed that the laws of physics are the same for all observers moving at constant speeds, and that the speed of light is constant for all of them. From these two simple postulates came a cascade of astonishing consequences. Time dilates. It stretches for those in motion relative to others. Length contracts. Distances shrink along the direction of motion, and mass, once thought fixed, increases with speed. None of this was speculation. It was a precise mathematical necessity. The equations predicted that as an object approached the speed of light, its mass would grow without limit, requiring infinite energy to go faster. The cosmic speed limit was absolute. No material object could reach or surpass the speed of light. For the first time, motion itself had boundaries defined not by force, but by geometry. The new theory also revealed the unity of energy and mass, expressed in Einstein's famous relation, energy equals mass, multiplied by the speed of light squared. This was not merely an equation, it was a statement about existence itself. Matter and energy were not different things, but two forms of the same underlying reality. A small amount of mass could contain an enormous amount of energy, and vice versa. The implications were profound. Time and space were no longer fixed stages upon which nature acted. They were active participants, bending and stretching with motion. The universe had lost its absolutes. Reality depended on the observer's frame of reference, yet the laws of physics remained consistent for all. It was a paradox only in appearance, a harmony revealed when one accepted that the universe's true symmetry included both space and time as parts of a single continuum. Einstein's revolution did not overthrow Newton, it expanded him. Newton's laws remained valid for slow speeds and weak gravitational fields, where relativity's corrections were too small to notice. But where motion approached the speed of light or fields grew strong, the old picture failed, and Einstein's vision took command. It was as though the world had been seen in sharp focus for the first time. Still, even as the new theory triumphed, one question remained unsolved. Special relativity described motion in the absence of gravity. But what about the force that ruled the stars? Newton's pull across empty space did not fit into Einstein's framework, for instantaneous action was forbidden. If nothing could travel faster than light, then gravity itself must obey that limit. Something deeper had to be hiding beneath Newton's equation, something that did not involve force at all. Einstein began to suspect that gravity was not a force pulling through space, but a feature of space itself. To uncover this, he would need to look at the universe in an entirely new way. not as a machine of parts, but as a geometry that could bend, curve, and twist. The next step would take him beyond motion into the very shape of reality. Einstein's ideas did not emerge from chaos, but from a deep simplicity. He believed nature was not built from arbitrary rules, but from underlying harmony. To him, beauty and logic were not luxuries of thought, they were clues to truth. When his paper on special relativity was published in 1905, it was not accompanied by grand announcements or experiments. It was quiet, mathematical, almost modest, yet its implications were seismic. It challenged the intuition of centuries, even as it explained the results that had puzzled physicists for decades. The world reacted slowly. At first, only a handful of scientists understood what Einstein had done. Hendrik Lorentz and Henri Poincaré had developed similar mathematical tools, but Einstein went further by discarding the ether entirely. He declared that there was no universal rest frame, no privileged point of reference. Motion, time, and length existed only in relation to other observers. This was not philosophy, it was measurable physics. The Michelson-Morley experiment, the behavior of charged particles, and the equations of electromagnetism all found their natural explanation within this new framework. One of Einstein's favorite thought experiments involved trains and lightning strikes. Imagine a train moving at high speed along a track. A flash of lightning strikes both ends of the train simultaneously according to an observer standing on the ground. But for a passenger on the train, moving toward one flash and away from the other, the light from the front strike reaches them later than the light from the rear. For that passenger, the two events are not simultaneous. Both perspectives are valid because the speed of light is the same for everyone. There is no single, universal now. Time itself is relative. This idea was revolutionary, not just in science, but in thought. The notion that time could flow differently for different observers seemed impossible, yet the mathematics made it unavoidable. Decades later, experiments with atomic clocks would confirm it. Planes flying around the Earth returned with clocks that had ticked at slightly different rates compared to those left on the ground. Particles known as muons, created in the upper atmosphere, survived longer than expected because they were moving near the speed of light, their internal clocks slowed by motion. What had once been theory became measurable fact. Special relativity also merged electricity and magnetism into a single entity viewed differently by different observers. What one person called an electric field, another might call a magnetic field, depending on their motion. This unity revealed that forces were not independent phenomena, but expressions of a single structure shaped by space and time. Nature was beginning to show its deeper simplicity. Still, Einstein could not rest. The new theory resolved the contradictions between mechanics and electromagnetism, but gravity remained outside its reach. Newton's gravity acted instantly, while relativity forbade anything from moving faster than light. The two ideas could not coexist. Einstein suspected that the answer lay not in adding new forces, but in rethinking the meaning of acceleration and gravity themselves. He began to notice an overlooked connection. When a person stands still on the surface of the Earth, they feel the pull of gravity holding them down. But when that same person falls freely, as in an elevator with its cable cut, the sensation disappears. The falling body feels weightless. To Einstein, this was more than coincidence. Perhaps gravity and acceleration were two sides of the same phenomenon. This thought became his guiding star. It would lead him beyond the boundaries of special relativity into a new theory that would redefine not only gravity, but the nature of spacetime itself. It was a journey that would take him 10 years of work, countless equations, and a partnership with the mathematics of curved surfaces. Geometry turned into the language of the cosmos. The path was not easy. Einstein often despaired at the complexity of the mathematics. He wrote to friends that he felt as though he were groping in the dark, guided only by intuition. Yet that intuition was extraordinary. Where others saw equations, Einstein saw meaning. He imagined light bending, clocks slowing and geometry itself twisting around massive bodies. Slowly, the idea took form. If motion could distort time and space, then perhaps mass and energy could do the same. The presence of matter might bend spacetime, and what we perceive as gravity might simply be the result of objects following the natural curves of that geometry. In such a world, planets would not be pulled by an invisible force. They would be moving along straightest possible paths, geodesics, in a curved spacetime shaped by the sun's mass. This was the seed of general relativity. It was the moment when gravity began to fade as a force and reappear as geometry. The simplicity of Newton's universe was giving way to a more profound vision, one where space and time were not passive backdrops, but living, dynamic entities intertwined with matter itself. Einstein's thoughts were still unproven, fragile yet luminous. The next step would demand courage and precision. He would need to show that the geometry of spacetime could reproduce every known prediction of Newton's gravity and explain the mysteries that Newton could not. The greatest transformation in the history of physics was about to begin. The years that followed were some of the most intense of Einstein's life. Between 1907 and 1915, he worked to transform his insight about gravity and acceleration into a mathematical theory of the universe. He had glimpsed a principle so simple that it bordered on the poetic, that a person in free fall experiences no gravity at all. From this thought, everything else would unfold. He called it the equivalence principle. Imagine a person inside a sealed room, floating in deep space, far from any planet or star. If the room begins to accelerate upward with constant speed, the person will feel pressed to the floor just as if they were standing on the earth. Drop a ball, and it will fall to the floor in the same way. The two experiences are indistinguishable. Gravity and acceleration are equivalent. To Einstein, this meant that gravity was not a mysterious force reaching out through the void, but a property of motion and geometry. He realized that if acceleration could mimic gravity, then perhaps gravity itself was a kind of acceleration caused not by a pull, but by the curvature of spacetime. Objects in free fall, planets, apples, even beams of light, are not being pulled at all. They are moving naturally, following the straightest possible paths in a curved geometry. What we feel as the force of gravity is merely our resistance to that natural motion. The Earth's surface prevents us from following our geodesic through spacetime, and we interpret that resistance as weight. Einstein's search for the mathematics to describe this curvature led him deep into geometry. He turned to his old friend Marcel Grossmann, a mathematician who guided him toward the tensor calculus developed by Gauss and Riemann. These tools allowed Einstein to describe how space could bend and stretch. Slowly, the pieces came together. Mass and energy tell space-time how to curve, and that curved space-time tells matter how to move. It was a relationship of mutual influence, elegant and complete. By 1915, after years of frustration and revision, Einstein presented his final field equations to the Prussian Academy of Sciences. They were simple in appearance, but immense in depth. On one side of the equation stood geometry, describing curvature. On the other stood the energy and momentum of matter. Together, they formed a bridge between the fabric of space-time and everything that occupies it. At first, few understood. Even Einstein's closest colleagues struggled with the mathematics, yet the meaning was clear. The universe was not a stage set upon which gravity acted. It was an active participant in the drama, changing and responding to matter and energy. Space and time were dynamic, fluid, alive. This new vision explained the lingering mysteries that Newton's laws could not. The strange precession of Mercury's orbit, which had resisted every correction, now emerged naturally from the curvature of spacetime around the Sun. The equations also predicted that light itself should bend when passing near a massive object, and that time should slow in strong gravitational fields. These were not philosophical musings, but measurable effects. Still, Einstein remained cautious. His theory was beautiful, but beauty alone was not enough. It needed proof, experimental, undeniable proof that the geometry of space-time was real. That evidence would come a few years later, during a rare celestial event when the sun would serve as the perfect laboratory for testing his prediction. As the Great War darkened Europe, Einstein worked in quiet defiance of despair. He was certain that nature would one day reveal the truth of his equations. In a world divided by conflict, he had discovered something universal, a law that bound every star, every planet, and every grain of dust into one continuous geometry. When he finally set down his pen, he had not merely rewritten Newton, he had redefined the universe. Gravity, once thought to be a force, had become a feature of space-time itself. The clockwork cosmos had turned into a living, elastic fabric, and the old absolutes of space and time had dissolved into a single, united reality. The next chapter in the story of gravity would begin not with equations, but with starlight, a test written across the sky that would show the world that space itself could bend. Imagine standing inside a room sealed from the outside world. You have no window, no sound, no hint of what lies beyond the walls. Suddenly, the floor presses against your feet, and a ball you release falls to the ground. You might assume that you are standing on a planet, and that gravity is pulling the ball downward. But if that same room were instead floating in empty space, being pulled upward by a rocket at constant acceleration, the ball would behave in exactly the same way. You would not be able to tell the difference. For Einstein, this thought was not a curiosity. It was a revelation. This idea, known as the equivalence principle, became the foundation of general relativity. It stated that being in a gravitational field is locally indistinguishable from being in an accelerated frame of reference. In a small enough region of space, gravity could be made to vanish by simply falling freely. To fall, Einstein realized, was to be weightless. Gravity was not something that pushed or pulled, but something that shaped motion itself. Einstein's insight was radical because it broke the final link to Newton's invisible force. For 2 centuries, scientists had treated gravity as a pull transmitted across empty space. But what if, Einstein wondered, there was no pull at all? What if the presence of mass and energy simply altered the structure of space-time, and what we felt as gravity was our response to that altered geometry? This idea turned the universe inside out. To grasp the equivalence principle, Einstein returned again and again to his thought experiments. He imagined an observer in free fall, such as a person leaping from a tall building or an astronaut orbiting the Earth. In that moment of fall, the observer feels no gravity. They and the objects around them move together, following the same natural path. It is only when motion is resisted, when the ground or the spacecraft's floor interrupts the fall, that the sensation of gravity appears. This simple observation contained the seed of an entirely new understanding of nature. If gravity could be transformed away by changing one's state of motion, then it could not be a fundamental force in the same sense as electromagnetism. Instead, it must arise from the way space-time itself behaves. Einstein's principle suggested that the geometry of space-time determines how objects move, and that matter, in turn, tells space-time how to curve. The interplay between matter and geometry would become the heart of general relativity. Einstein began working out the mathematics in earnest. He knew that describing curvature required more than ordinary geometry. He needed a language that could express how coordinates change when space itself bends. With help from his mathematician friend Marcel Grossmann, he turned to the field of differential geometry developed by Carl Friedrich Gauss and Bernhard Riemann. In this mathematical landscape, the shortest path between 2 points is called a geodesic, the generalization of a straight line on a curved surface. Just as a great circle on the Earth is the straightest possible path on a sphere, the motion of a planet around the Sun could be understood as a geodesic in the curved space-time created by the Sun's mass. No invisible force pulls the planet inward. Instead, spacetime's geometry guides its motion naturally along a curved path. The simplicity of the picture was breathtaking. But turning this insight into a theory required patience and precision. Einstein worked through countless pages of calculations, testing each version against the known facts of astronomy. He wanted his equations to reduce to Newton's laws under ordinary conditions, where gravitational fields are weak and speeds are slow, but also to predict new phenomena that Newton's theory could not. For years, he struggled to find the right form, equations that were both mathematically elegant and physically complete. Through all this, the equivalence principle remained his compass. He called it the happiest thought of my life. It told him that in a small enough region of spacetime, gravity disappears, and that locally, the laws of physics are those of special relativity. This meant that the effects of gravity are not mysterious actions at a distance, but manifestations of spacetime's shape over large scales. Einstein's vision was not yet proven, but it was coherent, logical, and testable. He had found a way to unite the geometry of space with the flow of time, to show that matter does not merely exist in spacetime, it creates it. The path from Newton's pull to Einstein's curvature had begun, guided by a single thought: that to fall is to be free. Einstein's equivalence principle did more than link gravity and acceleration. It redefined what it meant to move. In Newton's world, motion was measured against an absolute frame, a background of space and time that never changed. But in Einstein's emerging picture, there was no such stage. Space and time themselves were flexible, able to stretch, twist, and curve. Objects did not move through space-time, their motion was shaped by it. He began to picture the universe as a vast fabric, invisible yet real, in which matter and energy left imprints that guided every motion. A planet orbiting the Sun, for example, was not being pulled by an unseen hand. It was simply following the straightest possible path through the curved geometry created by the Sun's mass. To the planet, its motion was perfectly natural. It felt no force at all. What we interpret as gravity is merely the consequence of geometry. To make this concrete, Einstein thought in images. Imagine placing a heavy ball on a stretched rubber sheet. The sheet curves around the ball, and smaller marbles rolling nearby follow curved paths, not because they are attracted to the ball by a force, but because the surface itself directs their motion. Though the true geometry of space-time is four-dimensional and cannot be fully visualized, this simple analogy captures the essence. Mass tells space-time how to curve, and curvature tells mass how to move. The mathematics behind this vision was complex. With Grossman's help, Einstein explored Riemann's concept of metric tensors, mathematical objects that describe how distances are measured in curved spaces. The curvature of spacetime could be expressed using derivatives of these tensors, forming quantities that described how the geometry bends at each point. But the challenge was immense. Einstein had to connect this pure geometry to physical reality, to the energy and momentum of matter. He worked in solitude for years, filling notebooks with equations. The struggle was both intellectual and emotional. He wrote to his friends that he felt like a man climbing a mountain, certain of the summit but unsure of the path. Sometimes he believed he had found the correct formulation, only to realize that his equations failed to satisfy energy conservation or disagreed with observations. Each failure brought him closer to the truth. During these years, the equivalence principle served as his guiding test. Every version of his equations had to obey it. Wherever gravity could be eliminated by free fall, the laws of physics had to reduce to those of special relativity. This requirement kept his theory grounded in empirical consistency. It also meant that the geometry of spacetime had to behave locally like the flat geometry of special relativity, even if it curved on larger scales. Step by step, the pieces began to align. When Einstein applied his emerging equations to the orbit of Mercury, he found, to his astonishment, that the unexplained shift in its perihelion, the one that had haunted astronomers since the 19th century, emerged naturally from the curvature of spacetime around the Sun. No new planets, no invisible forces, only geometry. For the first time, the universe itself was speaking in the language of curves and geodesics, and its message matched observation perfectly. This success confirmed that Einstein was on the right path, yet it was not enough. He needed a general law, a precise mathematical expression linking the curvature of spacetime to the energy and momentum of matter. This equation would have to hold everywhere, in the void between stars and in the heart of massive bodies. The search consumed him. He walked the streets of Berlin lost in thought, whispering equations to himself. Friends recalled how he would pause mid-conversation, staring into nothing, then suddenly smile as if seeing some hidden order. Bit by bit, he assembled the framework. When at last he wrote down the equation that satisfied all his criteria, he recognized it immediately. It was not only correct, it was inevitable. Gravity was no longer a mysterious force acting across the void. It was the manifestation of space-time curvature, created by mass and energy and experienced by every object as the geometry of its path. Einstein had transformed our understanding of motion and space, uniting them into a single, elegant fabric, where falling is simply the art of moving straight in a curved world. But even this profound idea needed proof beyond the realm of mathematics. The next test would come not from equations, but from the heavens themselves, from a natural experiment written in the light of distant stars. Einstein knew that the true power of his theory would be proven not in thought experiments, but in nature itself. The universe, after all, was the ultimate laboratory. If space-time could truly bend and curve, its effects had to be visible somewhere beyond the pages of mathematics. He turned again to the stars. One of the clearest predictions of his theory was that light should follow the curvature of space-time just as planets do. In Newton's view, light had no mass and therefore could not be affected by gravity. But if gravity was not a force and instead a property of geometry, then the path of light would naturally bend when it passed near a massive body. The deflection would be tiny, almost impossible to detect, but measurable during a total solar eclipse, when the sun's glare was hidden and the stars near its edge became visible. Einstein calculated the amount of bending his theory predicted, roughly twice as much as Newton's equations suggested. The difference was small, yet it carried enormous significance. It was not just a correction to Newton's law, it was evidence that gravity was not acting at a distance, but shaping the very space through which light traveled. But before such an observation could be made, the world was torn apart by war. From 1914 to 1918, Europe descended into the chaos of the Great War. Einstein, isolated in Berlin, continued refining his equations while the continent burned. Despite the turmoil, his focus never faltered. In November of 1915, he presented the final form of his field equations to the Prussian Academy of Sciences. The theory was complete. He had done what no one before him had achieved. He had merged space, time, matter, and energy into one self-consistent description of the universe. The equations could describe everything, from the motion of planets to the path of light and the slowing of time in strong gravitational fields. The universe was now a dynamic geometry, responsive and alive. Einstein understood the philosophical depth of what he had uncovered. The human notion of force, the idea that something pulls or pushes, was merely a projection of our limited perspective. What we call gravity was simply the natural motion of things in curved space-time. The apple does not fall because the Earth pulls it down. It falls because space-time guides it toward the Earth's center along a geodesic. The concept of attraction is replaced by geometry, and space itself becomes the unseen architect of motion. For centuries, humanity had pictured the cosmos as a clockwork of forces. Einstein replaced that with a vision of harmony, a universe that moves not through mechanical pushes, but through the elegance of shape. The equivalence principle, born from the simple realization that free fall and weightlessness are the same, had grown into one of the most profound insights ever conceived. Even as his theory gained mathematical perfection, Einstein knew that the world would need to see proof with its own eyes. The eclipse observation that could confirm the bending of starlight would not come until after the war, but he was certain of the result. To him, the equations already spoke the truth. "The theory is beautiful," he wrote to a friend, "and therefore I am sure it is right." When the guns of war finally fell silent, the stage was set for that proof. A new generation of astronomers would look to the sky, not to chart new planets or measure old orbits, but to test whether space itself could bend the light of distant stars. What they would find would change the course of physics forever and turn Einstein from a quiet mathematician into a name known across the world. The age of Newton's gravity had ended. The age of spacetime had begun. The year was 1919. Across the world, nations were still recovering from the devastation of war. Cities lay in ruins, empires had fallen, and a generation had been lost. Yet, as the smoke of conflict cleared, a different kind of battle, a battle of ideas, was about to reach its moment of truth. In that year, the cosmos itself would serve as witness to a test that could confirm or shatter the greatest theory of gravity ever conceived. Albert Einstein's general theory of relativity had been published only a few years earlier. It was elegant, revolutionary, and, to many, almost impossible to believe. He had claimed that gravity was not a force acting across space, but the curvature of space and time itself. To prove it, one needed evidence that this curvature was real, that it could bend not just the motion of planets, but even the path of light. And the universe, as if waiting for its cue, offered a rare opportunity to find out. A total solar eclipse was predicted for May of 1919, its path crossing parts of South America and West Africa. During those few precious minutes when the moon would block the sun, the stars around the darkened disk would become visible. According to Einstein's equations, their apparent positions would shift slightly outward, the light from each star deflected by the curved spacetime around the sun. The predicted deflection was small, about 1.75 arcseconds, yet measurable with the finest photographic instruments of the day. Newton's theory predicted only half that value. The difference between the two would determine whether space itself could truly bend. The challenge of testing such a prediction fell to a quiet British astronomer named Arthur Eddington. A devout Quaker and a believer in the power of reason over conflict, Eddington saw in Einstein's work not just a scientific breakthrough, but a symbol of unity. Here was a theory from a German physicist being tested by British scientists in the aftermath of war. Proof that truth transcended nations. Eddington prepared 2 expeditions. One would travel to the island of Príncipe off the coast of West Africa, while another would observe from Sobral in Brazil. Both teams carried delicate telescopes, cameras, and instruments designed to capture the positions of stars near the sun's edge during the eclipse. To compare these photographs, Eddington would also record the same stars at night months later, when the sun had moved to another part of the sky. Any shift in their apparent positions would reveal how much their light had been bent. As the day approached, anxiety mounted. Clouds, equipment failures, or even a sudden storm could destroy years of preparation. On May 29th, the sky darkened over Príncipe. For a tense few minutes, the moon's shadow swept across the land, and the stars near the sun flickered into view. Eddington and his assistants worked silently, exposing photographic plates by hand, timing each frame as if the entire weight of science rested on those few seconds. Then, just as quickly as it began, the light returned, and the opportunity was gone. Weeks passed before the fragile plates could be developed and measured. Back in England, Eddington compared his results with those from Brazil. The measurements were painstaking. The The differences between the predicted positions and the observed ones were tiny, barely the width of a pinhead. Yet when the data were combined, the result was clear. The deflection matched Einstein's prediction almost exactly. The starlight had bent not by Newton's value, but by Einstein's. Space itself had curved. That moment transformed Einstein from a name known only to physicists into a symbol recognized around the world. The newspapers declared a revolution in science. "Lights all askew in the heavens," one headline read. The image of a universe bending under the weight of matter captured the public imagination. Overnight, the quiet patent clerk from Bern became a legend, his face as familiar as any monarch's. But for Einstein, the result was not about fame, it was about truth. For the first time, nature had spoken in the language of geometry, confirming that the fabric of space-time was real and measurable. Gravity was no longer an invisible pull, it was the shape of reality itself. Still, Einstein remained characteristically calm. When asked how he would have reacted if the experiment had disproved his theory, he replied with quiet humor, "Then I would have felt sorry for the dear Lord. The theory is correct." His confidence was not arrogance, it was trust in the logic of nature. The world, meanwhile, was beginning to realize what his discovery meant. If space-time could bend, then time itself could slow near massive bodies. Clocks would tick differently depending on where they stood in a gravitational field. The geometry of existence was no longer uniform. The familiar world of flat space and steady time had dissolved into a flexible, dynamic continuum. For the first time in human history, light had traced the invisible contours of gravity. The eclipse of 1919 had not only confirmed a theory, it had revealed the living structure of the cosmos. In the weeks that followed the eclipse, the world changed in ways that even Einstein could not have imagined. Newspapers from London to New York filled their front pages with astonishment. Headlines declared that Newton's laws had been overturned and that a new vision of the universe had emerged. "Revolution in science," wrote the Times of London. "New theory of the universe, Newtonian ideas overthrown." Scientists, philosophers, and ordinary readers alike found themselves looking upward with renewed wonder. For centuries, Newton's gravity had described a cosmos of perfect predictability, planets circling the sun under a silent, invisible force. Now that cosmos had become dynamic, space was no longer passive emptiness, and time was no longer uniform. The two were joined, alive, and responsive to the presence of matter. The universe had acquired a kind of flexibility, as though reality itself could stretch, warp, and ripple. Eddington's measurements were soon checked and rechecked. Despite minor uncertainties caused by atmospheric conditions, the outcome remained unchanged. The starlight near the sun had bent precisely as Einstein predicted. This bending was not an optical illusion or an effect of the atmosphere. It was the unmistakable signature of curved space-time. The universe had spoken, and it had spoken through geometry. The experiment's success carried a meaning far beyond science. After the destruction of the Great War, humanity was searching for unity, for something larger and enduring than its divisions. Here was a theory from a German scientist, verified by British astronomers, proving a universal truth that transcended nations. It was a moment of reconciliation between intellect and imagination, between the human mind and the cosmos it sought to understand. Einstein received letters from around the world, from philosophers, artists, theologians, and curious citizens, all asking what it meant that space could bend and time could flow differently. His image appeared in newspapers beside diagrams of warped grids and circles of light curving around the sun. For the first time, a concept of pure mathematics had entered the realm of common understanding. People might not have grasped the details, but they felt the magnitude of the discovery. Reality was not what it seemed. Yet Einstein himself remained modest. He insisted that Newton's laws were not wrong, but incomplete. For the conditions of ordinary life, falling apples, rolling carts, or orbiting moons, Newton's equations remained excellent approximations. But near the extremes, where gravity grew strong or motion approached the speed of light, the deeper geometry revealed itself. Newton's cosmos was a chapter within Einstein's, not a rival to it. As astronomers repeated their measurements over the next decades, the evidence only grew stronger. The bending of light was observed again during later eclipses, confirmed with radio waves, and eventually measured with such precision that the uncertainty dropped to a fraction of a percent. Every test told the same story. The geometry of spacetime was real, and general relativity worked. This triumph did not mark an end, but a beginning. Einstein's equations hinted at possibilities that extended far beyond the Sun and its planets. They allowed for the existence of regions where curvature could grow without limit, where light itself could become trapped. They suggested that time could slow almost to a stop in extreme gravitational fields. The theory predicted not just how stars shine and die, but how the universe might have begun and how it might one day end. Still, at the heart of this vast framework lay a simple truth: the equivalence principle that had guided Einstein from the start. The weight you feel under your feet is not the pull of a distant force, but the gentle curvature of spacetime pressing against you. The sun does not hold the Earth through invisible strings. It shapes the geometry in which the Earth moves. Every motion, every orbit, every fall is a response to that shape. Einstein often reflected on how strange it was that such an idea could be captured in pure mathematics and then confirmed by looking at starlight. The simplicity of the result concealed the depth of its meaning. For the first time, humanity had measured not a substance or a force, but the very structure of reality itself. The eclipse of 1919 was not merely an event in the sky, it was a turning point in the human story. It had shown that the universe could no longer be explained by the language of forces and fields alone. Instead, it spoke in the language of curvature, geometry, and time. Einstein's theory had predicted it all, and now the cosmos had answered. The path ahead would lead to wonders and paradoxes, even stranger than curved light, to warped time, collapsing stars, and horizons from which no signal could ever escape. The door to the next era of discovery had opened, and humanity had only just stepped through. The confirmation of Einstein's prediction was more than a scientific milestone. It was a philosophical awakening. The eclipse of 1919 had shown that the universe was not static or mechanical, but dynamic, curved, and responsive. The geometry of space-time had stepped out of mathematics and into the light of observation. For the first time, humanity had seen space itself act. In the months that followed, the idea spread far beyond the scientific community. Writers, artists, and philosophers began to weave relativity into their own work, seeing in it a metaphor for a changing world. The war had shattered old certainties, and now physics had done the same. Time was no longer universal. Space was no longer absolute. Reality itself depended on perspective. What had once been a cold and predictable cosmos now felt alive, flexible, and strange. But among scientists, the reaction was more careful. Many still doubted that a theory so radical could be correct. Some questioned the precision of Eddington's measurements, suspecting bias or error. Others simply found it difficult to abandon Newton's clarity for Einstein's curvature. For generations, physics had been built upon the intuition that space and time were firm foundations. To imagine them bending and twisting required a leap of thought that few were ready to take. Einstein, meanwhile, remained patient. He understood that new ideas must earn their place through evidence, not persuasion. He welcomed further tests, certain that nature would continue to affirm the geometry he had uncovered. Over the years, each experiment added a new piece of confirmation. The gravitational redshift of light was detected. The slowing of time in strong gravitational fields was measured. Eventually, The accuracy of modern instruments, from atomic clocks to satellites, would depend on the very corrections predicted by general relativity. Even then, Einstein's view of his achievement remained humble. He saw himself not as a destroyer of Newton's work, but as its continuation. Newton had described how objects moved under the influence of gravity. Einstein had explained what gravity truly was. Together, their ideas formed a seamless progression, a deeper understanding of the same cosmic order. Where Newton saw a force, Einstein saw geometry. Where Newton saw motion, Einstein saw structure. In public lectures, Einstein spoke softly, but with conviction. He often compared the curvature of spacetime to the surface of the Earth. To those walking across it, the planet feels flat. Only when one looks from a distance does its roundness become clear. In the same way, the curvature of spacetime is invisible in everyday life, but under the gaze of mathematics and starlight, its shape reveals itself. The eclipse had shown that the universe was not just a collection of objects moving through emptiness. It was a continuous fabric that could warp, bend, and ripple. Every star, every planet, every atom played a role in shaping that fabric. Gravity was not something added to the universe. It was the universe's very architecture. This new vision carried with it a sense of awe. To live in a curved cosmos meant that existence itself was interconnected. The motion of one body could subtly affect the path of another across infinite distances, not by pulling, but by shaping the space between them. The cosmos was not mechanical, it was relational. For Einstein, the confirmation of his theory did not bring an end to curiosity, but a new beginning. His equations hinted at possibilities so extreme that even he hesitated to believe them. Among their solutions were objects of unimaginable density, where space-time could curve infinitely. What would later be called black holes. The equations also suggested that the universe itself might not be eternal and unchanging, but expanding or contracting like a living organism. Those implications would take decades to explore, but the foundation had been laid. The eclipse of 1919 was the proof of principle, the first experimental glimpse of the deep structure of reality. From that moment onward, no serious physicist could think of gravity as a mere force again. As the 20th century unfolded, Einstein's curved spacetime would become the language through which we described not only stars and galaxies, but time itself. His theory, born from the simple act of imagining a person falling freely, had changed humanity's relationship with the cosmos. The light that bent around the sun that day did more than confirm an equation. It illuminated a truth that would echo through every discovery to come. That gravity is not the hand that moves the universe, but the shape through which the universe moves. By the time the world recognized Einstein's theory as the new foundation of gravity, the heart of his discovery, the mathematics that made it possible, had already been written in elegant strokes of logic and geometry. It was a language so abstract that only a few minds of the time could read it fully. Yet within its symbols lay the structure of the universe itself. These were the Einstein field equations, a set of relations that connected the shape of space-time to the energy and momentum it contained. Einstein had reached them after years of struggle. For almost a decade, he searched for the precise expression that could translate the curvature of space-time into measurable physical effects. He knew what the equations must do. They had to describe how matter tells space-time how to curve, and how curvature tells matter how to move. They had to honor the principle of equivalence, reducing to special relativity where gravity vanished, and to Newton's law where fields were weak. They had to be beautiful, simple, and universal. The result he finally presented in November 1915 was deceptively compact. In modern notation, it is written as G equals 8 pi times G divided by C to the power of 4 multiplied by T. On one side stands geometry, represented by a tensor known as G, which describes the curvature of spacetime. On the other side stands matter and energy, represented by another tensor, T, which encodes how energy and momentum are distributed. The equation declares that these two are inseparable. The geometry of the universe is shaped by the matter within it, and the motion of matter follows that geometry. Though the symbols look cryptic, their meaning is profound. In simple terms, they say that space-time is not a passive container, but a dynamic fabric whose shape changes with every transfer of energy. The presence of mass, light, or pressure alters this shape, bending the paths of objects and even the flow of time. In this sense, gravity is not a field that exists within space-time. It is space-time. Einstein had turned the mystery of attraction into an equation of geometry. Newton's force had become curvature, and distance itself was no longer absolute, but part of a living system. The field equations could describe everything from the orbit of a planet to the expansion of the entire universe, using the same mathematical structure. To visualize this, one can imagine space-time as a flexible sheet. When a massive body like the Sun rests upon it, the sheet dips gently, creating a curvature. Smaller bodies, like planets, follow the natural curves of that surface. They are not being pulled, but are simply moving straight within a geometry that is no longer flat. The equation tells us exactly how deep that dip will be, depending on the mass and energy of the object. Einstein was astonished by how quickly the mathematics produced verifiable predictions. The precession of Mercury's orbit, which had defied all classical explanations, fell neatly into place within the new framework. The theory also implied that time itself slows down near massive bodies, a consequence of space-time curvature that would later be confirmed by precision clocks. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths, a phenomenon now called gravitational redshift. Each of these effects emerged naturally from the same set of equations. For Einstein, this unity was proof that he had found something fundamental. The theory did not rely on assumptions or hidden mechanisms. It described what space, time, and matter are, not just how they behave. In his equations, reality itself became self-consistent, a seamless conversation between geometry and energy. And yet, as elegant as the mathematics was, it carried an unsettling depth. The equations admitted solutions that Einstein himself hesitated to accept, strange possibilities that seemed to stretch the imagination beyond reason. Some of those solutions described regions where space-time could curve so strongly that even light could not escape. Others hinted that the universe might not be static, but expanding or contracting. Einstein, cautious and rational, initially resisted these extremes. He believed the universe must be balanced and eternal. To keep it so, he added a term to his equations, the cosmological constant, designed to hold the cosmos steady against collapse or expansion. He would later call this his greatest blunder, though in truth, it was a doorway to discoveries that would emerge decades later. At the time, however, what mattered most was that the field equations worked. They described the physical world with extraordinary precision and provided a framework that would guide physics for the next century. Einstein had succeeded in capturing the invisible architecture of reality in a single mathematical statement, a link between geometry and existence. But the universe had not yet revealed the full power of those equations. Within their quiet symmetry lay predictions far stranger than curved light or slowed time. As physicists began to explore their implications, they would uncover the most extreme objects ever imagined. Stars so dense that space itself could no longer remain open, where time would seem to come to a stop. The equations had spoken, and the cosmos would soon show what they truly meant. The elegance of Einstein's field equations was matched only by their depth. For those who could read them, they described the heartbeat of the universe itself, the balance between matter and geometry, energy and time. Yet their very simplicity concealed astonishing power. With the right assumptions and the right boundary conditions, they could describe not only stars and planets, but the birth, death, and shape of the cosmos. When Einstein first presented his equations, few understood how vast their implications were. Even he did not grasp at once the full range of worlds hidden within them. But soon, other physicists began to explore their consequences, discovering that these 10 interwoven equations were far more than a refinement of Newton's law. They were a new language of nature. One of the earliest and most striking results came from a young German physicist named Karl Schwarzschild. In 1916, while serving on the front lines of the First World War, he managed to solve Einstein's equations for the simplest possible case: a single spherical mass in otherwise empty space. His solution revealed that space-time around such a body curved in a specific way, described by what is now called the Schwarzschild metric. The mathematics showed that if a mass were compressed into a small enough region, its gravitational field would become so intense that not even light could escape. Einstein at first dismissed this as a mathematical curiosity, believing such an extreme object could never exist in nature. Yet decades later, these solutions would be recognized as the first precise description of black holes. The geometry itself predicted them long before they were observed. Even without such extremes, the field equations quickly proved their power. When applied to weak gravitational fields like those near Earth, they reduced neatly to Newton's familiar law. In stronger regimes, around massive stars or near the Sun, they predicted measurable deviations that experiments would later confirm with uncanny accuracy. Every test strengthened confidence in Einstein's vision. One of the most beautiful aspects of the theory was its universality. The same equations that described the motion of planets also governed the bending of light, the slowing of time, and even the evolution of the universe. By including all forms of energy, mass, radiation, pressure, the equations made no distinction between material and immaterial sources of gravity. A beam of light could curve space just as a planet could, though its influence was faint. Everything that carried energy contributed to the curvature of space-time. To visualize the field equations, imagine the universe as a vast, four-dimensional fabric. Each thread represents a direction in space or time. When matter or energy passes through, it pulls gently on the threads, distorting the weave. Those distortions change how other threads run, guiding the paths of planets, light, and time itself. The pattern never stays fixed. With every motion of a star or pulse of radiation, the geometry adjusts, rippling outward at the speed of light. This dynamism was unlike anything in classical physics. Newton's space had been eternal, unchanging, indifferent to the matter within it. Einstein's space-time was alive. It could vibrate, distort, and carry information across the cosmos. The theory predicted that violent cosmic events, the collision of massive bodies or the collapse of stars, would send waves of curvature spreading outward, like ripples on a pond. These gravitational waves would be faint, nearly impossible to detect with the technology of Einstein's time, but they were inevitable consequences of the equations. Another consequence was even more profound. When physicists such as Alexander Friedmann and Georges Lemaitre applied Einstein's equations to the universe as a whole, they found that the geometry could not remain static. If the cosmos contained matter and energy, it must either expand or contract. Einstein had resisted this conclusion, introducing his cosmological constant to preserve stability. But in 1929, the astronomer Edwin Hubble observed that distant galaxies were receding from us. Their light stretched toward the red. The universe was expanding, just as the equations had predicted. Einstein's so-called blunder turned out to be a glimpse of something deeper, the possibility that space-time itself could grow, carrying galaxies along like raisins in rising bread. Each new discovery revealed that Einstein's mathematics was not a narrow description of a few celestial mechanics, but a map of all physical reality. It described how stars burn and die, how light travels, how time flows differently near mass, and even how the cosmos evolves on its largest scales. It was both a theory and a philosophy, the idea that geometry and existence are one. The precision of the field equations continues to astonish physicists even today. Whether tested in the orbit of Mercury, in the bending of starlight, or in the faint signals of pulsars, they have never failed. Every observation reaffirms the same truth. Gravity is not a force in the Newtonian sense, but the shape of space-time itself, sculpted by energy and matter. Yet, within that same perfection lay a mystery that even Einstein could not ignore. The equations could describe everything except their own limits. They predicted regions where curvature could grow infinite, where time could stop, and where the known laws of physics could no longer apply. These singularities, as they came to be called, were not mathematical accidents. They were built into the very structure of the equations. The geometry that explained the heavens was also hinting at places where understanding would fail, the edges of knowledge itself. Einstein's field equations, elegant and precise, had unified the fabric of space, time, and matter. Yet they also carried within them an unsettling prophecy that under certain conditions, space-time could fold in on itself, producing regions where the known laws of physics would cease to function. The very equations that explained how the universe worked also foretold the places where it would break down. At first, Einstein did not believe that nature would permit such extremes. He saw the singularities that arose in the mathematics as artifacts, imperfections in the equations, or the result of oversimplified assumptions. But the equations themselves disagreed. When later physicists examined them carefully, they found that singularities were not rare accidents. They were inevitable outcomes when enough mass was packed into a small enough volume. To understand how this happens, imagine a star far more massive than the Sun. Throughout its life, the star burns hydrogen into helium, its radiation pressure balancing the inward pull of gravity. But when its fuel is exhausted, the radiation stops and gravity has no opposition. The star begins to collapse under its own weight. According to Einstein's equations, if the mass is large enough, no known force can halt that collapse. The geometry of space-time curves ever more steeply until the surface of the star passes a critical point, a horizon beyond which light itself cannot return. Inside that horizon, space-time collapses completely into a singularity, a region of infinite curvature where time and space lose their meaning. This was not speculation. It was the exact solution discovered by Carl Schwarzschild and later expanded upon by generations of physicists. The mathematics was clear. Black holes were not just possible, they were required. The universe, once thought smooth and continuous, contained places where geometry ended. Even as these predictions emerged, the practical world seemed distant from them. Einstein himself doubted that nature would ever allow a star to collapse so completely. Yet, as astronomical technology improved, the evidence began to mount. In the mid-20th century, strange sources of intense X-rays and radio waves were discovered, their behavior unlike any known object. Eventually, the patterns of motion around them, the gravitational lensing of light, and the emission of high-energy radiation confirmed what the equations had said all along. Black holes were real, not mathematical abstractions, but cosmic structures carved by geometry itself. Still, for every question answered, a deeper one appeared. What lies at the center of a singularity? The equations predicted infinite density, but infinity is not a physical quantity. It marks the boundary where theory fails. Inside that region, the smooth space-time of relativity would have to give way to something else, a quantum description that Einstein's equations could not provide. The marriage between gravity and the quantum world had not yet been written, and the singularity was its reminder. Beyond these extremes, the field equations also described the gentle curvature of the everyday universe. They told us why clocks run slightly faster at mountaintops than at sea level, why satellites orbiting the Earth must correct their time to maintain the precision of global positioning systems. They explained the way light from distant galaxies bends around clusters of matter, creating cosmic lenses that magnify what lies beyond. Every one of these effects, no matter how small, was a manifestation of space-time curvature, the living evidence that geometry rules the cosmos. To Einstein, these confirmations were both satisfying and humbling. He had replaced Newton's force with something deeper, yet he knew he had not reached the final truth. His equations described how space-time behaves, but not why it exists in the first place, or how it interacts with the discrete quanta of energy that rule the microscopic world. He would spend the rest of his life seeking a unified theory, one that could join gravity with electromagnetism and the emerging field of quantum mechanics. The search would remain unfinished. But what Einstein had already achieved was monumental. His field equations had transformed the very idea of reality. They told us that space is not an emptiness, time is not a river flowing independently of the world, and gravity is not a force acting at a distance. The universe, in his vision, was a single, interconnected geometry, elastic, responsive, and profound. From the orbit of planets to the motion of galaxies, from the ticking of a clock to the bending of starlight, everything followed from the same principle. Energy and matter shape the structure of space-time, and space-time shapes the motion of energy and matter. In those simple, silent symbols, G equals 8 pi times G divided by C to the power of 4, multiplied by T, Einstein had captured the relationship between existence and geometry. The cosmos was no longer a machine of forces, but a harmony of shapes, a continuous conversation between what is and where it is. And yet, within that harmony, the equations hinted at the unimaginable. If space-time could bend, it could also tear. If it could ripple, those ripples might travel across the universe. If it could collapse, it could give birth to the darkest objects ever known. The next step would be to confront those extremes, to follow the equations into the heart of gravity's greatest mystery, where curvature becomes infinite and time itself begins to unravel. In the quiet perfection of Einstein's field equations lay a hidden warning. If matter became too dense, if space-time curved too sharply, the elegant balance between geometry and energy would shatter. The equations did not break. They simply predicted their own limits. What emerged from that limit was something so strange, so absolute, that it would take humanity decades to accept it as real. These were the singularities, and the objects they formed would later be known as black holes. The idea of a star collapsing under its own gravity was not new. Even in the 18th century, thinkers such as John Michel and Pierre-Simon Laplace had speculated about dark stars, bodies so massive that light could not escape. But their reasoning was purely Newtonian, built on the notion of escape velocity. The concept was fascinating but remained theoretical, a curiosity of mathematics, not of nature. Einstein's general relativity changed that forever. When Karl Schwarzschild, stationed on the Russian front during the First World War, solved Einstein's equations for a single spherical mass, he revealed that space-time around such a body could be described with precise geometry. This geometry contained a radius, now called the Schwarzschild radius, where the curvature became so strong that the paths of all light turned inward. Beyond that boundary, called the event horizon, no information could return. It was not a surface of matter, but a point of no return, a horizon separating the observable universe from a region where time and space exchanged roles. Einstein initially refused to believe this could exist in the real cosmos. He thought nature would find a way to prevent such collapse. To him, singularities were mathematical artifacts, not physical entities, yet the mathematics was relentless. The equations demanded that if enough mass were concentrated in a small enough space, no known force could stop the collapse. The fabric of space-time itself would be pulled downward into an ever-deepening well. It took several decades and the rise of stellar astrophysics for this idea to gain traction. In the early 20th century, scientists began to understand how stars lived and died. They learned that when a star exhausts its nuclear fuel, the outward pressure from fusion can no longer resist gravity. Smaller stars cool into white dwarfs, held up by quantum pressure among their electrons. More massive stars compress further into neutron stars, supported by the resistance of their dense nuclear matter. But above a certain mass, roughly 3 times that of the Sun, even that resistance fails. Gravity wins completely. What happens next is not an explosion or a slow fading. It is a collapse so complete that the very notion of space inside the star ceases to have meaning. All the mass is drawn into an infinitely small region, a singularity, hidden behind the event horizon. For any external observer, time appears to slow as the collapsing surface approaches the horizon, freezing at the edge. But within the horizon, time continues relentlessly inward, as if all paths, all futures, end at the same point. This description might seem impossible to imagine, yet it flows directly from Einstein's mathematics. The black hole is not a hypothetical curiosity. It is the simplest, purest expression of gravity. It is geometry taken to its ultimate form. The black hole does not exert a force in the conventional sense. Instead, it reshapes space-time so completely that all trajectories, even those of light, curve inward. It is not an object within space. It is a region where space itself falls inward faster than anything can escape. The paradox of such a place captured the imagination of physicists and philosophers alike. Inside the horizon, the normal order of cause and effect is replaced by inevitability. Once crossed, no path leads outward again. Information, matter, and even light vanish from the visible universe, leaving only their gravitational imprint behind. To an observer outside, the black hole is defined not by what it contains, but by what it hides. For much of the 20th century, this remained a theoretical realm. The mathematics was precise, but direct evidence was lacking. Astronomers could not see black holes, only infer them. Yet, as telescopes grew more sensitive and technology advanced, the cosmos began to reveal their traces. Strange sources of X-rays flickered in the sky, their intensity varying in ways that matched matter spiraling into an unseen abyss. Stars were observed orbiting empty points in space with speeds that betrayed the presence of invisible giants. The predictions of relativity, once confined to paper, were coming alive in the heavens. What had once seemed like a mathematical impossibility was now becoming a central fact of cosmic structure. The universe was not merely dotted with stars and galaxies. It was threaded with these silent wells of geometry, each one a region where Einstein's equations ruled completely and human intuition failed. The story of black holes is the story of gravity taken to its absolute extreme. Every principle Einstein had uncovered, the curvature of space-time, the unity of mass and geometry, the slow ticking of time in strong fields, all reached their final dramatic expression within these invisible regions. Here, the theory that described the entire cosmos folds back upon itself, revealing both its perfection and its limits. By the mid-20th century, what had once been pure mathematics began to merge with observation. In the 1960s, astronomers discovered objects that radiated immense bursts of X-rays from small, compact regions. One of the first was Cygnus X1, a binary system where a visible star orbited an unseen companion. The orbit's speed implied a mass far too great and too dense to be a normal star, or even a neutron star. The only explanation consistent with the data was a black hole, the very entity that Einstein's equations had predicted decades earlier. Soon, similar evidence appeared throughout the sky. Some galaxies emitted jets of radiation stretching thousands of light years, powered by central engines invisible to optical telescopes. The energy output was staggering, yet the source was small enough to fit within our solar system. The only mechanism capable of releasing such power was matter falling toward a black hole, converting gravitational energy into radiation as it spiraled inward. General relativity had escaped the realm of theory and entered the language of astronomy. These discoveries revealed something profound. Black holes were not rare curiosities hiding in the corners of the universe. They were essential features of its structure. Stellar black holes mark the deaths of massive stars, while far larger ones, millions or even billions of times the mass of the Sun, sat at the centers of galaxies, shaping their evolution. The Milky Way itself revolves around such a giant, known today as Sagittarius A star. Its presence can be inferred from the rapid orbits of nearby stars, which race around an unseen center, as though pulled by an invisible gravity well. The geometry around these cosmic giants behaves in ways that defy everyday understanding. Near the event horizon, time slows dramatically. A second experienced by an observer falling toward the horizon could stretch into centuries when measured by someone far away. Space and time trade roles. To move forward in time within the horizon is to move inevitably toward the singularity. There is no force to resist, no surface to strike. Only the smooth flow of space-time carrying everything inward. Yet despite their darkness, black holes are not entirely silent. As matter spirals in, friction and compression heat it to millions of degrees, causing it to radiate intensely before crossing the horizon. In this way, black holes can light up the universe even as they consume it. Their surroundings become some of the brightest regions in existence, visible across billions of light years. In the 1970s, a new and unexpected insight came from Stephen Hawking. By applying quantum theory to curved space-time, he showed that black holes are not perfectly black. Tiny fluctuations in the vacuum near the horizon allow them to emit a faint glow of thermal radiation, what we now call Hawking radiation. Over immense spans of time, this radiation would cause a black hole to lose mass and eventually evaporate. The revelation linked gravity, quantum physics, and thermodynamics, suggesting that black holes were not just endpoints, but participants in the grand exchange of energy and information. The implications were staggering. Einstein's geometry had led to objects that challenged not only classical ideas of gravity, but the very foundation of physics. If black holes could evaporate, what happened to the information carried by everything that fell in? Did it vanish, defying the principle that information must be conserved? Or did it somehow remain encoded in the structure of space-time itself? These questions, born from the meeting of relativity and quantum mechanics, remain at the frontier of modern research. Meanwhile, the evidence for black holes continued to grow. In 2019, the Event Horizon Telescope, a network of observatories spread across the globe, captured the first image of a black hole's shadow, a glowing ring of light encircling darkness at the center of the galaxy M87. The image was more than a scientific triumph. It was a direct glimpse of space-time's curvature made visible. The light around the shadow had been bent by gravity into a circle, confirming with astonishing accuracy the predictions of Einstein's theory. To see that image was to witness the geometry of the universe revealed by its own light. It showed that Einstein's field equations, written over a century earlier, could describe reality with a precision beyond imagination. The black hole was no longer a symbol of mystery alone. It was a confirmation of understanding, a living proof of relativity's power. And yet, for all that it confirmed, it also reminded humanity of how much remains unknown. At the heart of every black hole lies a singularity, a region where the known mathematics ceases to function, where density and curvature rise without limit. It is a place beyond prediction, beyond even the concept of time. To understand what happens there, one must go beyond general relativity to a theory that unites the smooth fabric of space-time with the grainy texture of the quantum world. The black hole, then, stands as both an end and a beginning, the point where Einstein's vision reaches its greatest success and encounters its deepest challenge. It is gravity stripped to its essence, where space and time themselves become the phenomena that collapse. At the heart of a black hole lies a paradox so profound that it unsettles even the most seasoned physicists. According to Einstein's equations, the collapse of a massive star compresses matter into a single point of infinite density, a singularity where the curvature of spacetime becomes infinite. Time, space, and all known physical quantities lose their meaning there. Yet the universe does not tolerate infinities easily. Whenever equations predict them, it is nature's way of telling us that our understanding is incomplete. The singularity is not a physical point one can reach. It is the limit of the geometry itself, the place where the very fabric of reality ceases to provide answers. Within that horizon, all possible paths lead inward. Nothing, not even light, can escape. For an observer outside, the horizon is a perfect boundary. No message, no signal, no hint of what lies beyond can ever return. To cross that edge is to leave the observable universe entirely. Einstein's theory describes everything up to that boundary with perfect accuracy. The orbits of stars around black holes, the bending of light near their edges, the time dilation measured by satellites passing close to massive bodies, all match the predictions of general relativity precisely. But the singularity remains outside its reach. It is there that quantum mechanics, the theory governing the smaller scales of nature, must step in. The conflict between relativity and quantum mechanics defines the deepest problem in modern physics. Relativity treats spacetime as smooth and continuous, while quantum theory insists that energy and information come in discrete units. In most circumstances, these two frameworks coexist peacefully. But at the singularity, where gravity becomes infinitely strong and distances shrink to zero, their coexistence breaks down. The equations diverge, leaving a blank space where understanding should be. Physicists have spent decades searching for a theory that can unite the two. Some look to loop quantum gravity, which attempts to describe spacetime itself as made of tiny, discrete loops, replacing the continuum with a network of quantized geometry. Others pursue string theory, proposing that all particles and forces, including gravity, arise from vibrating one-dimensional strings within higher dimensional spaces. Though each approach remains incomplete, they share the same ambition: to reveal what happens when curvature and quantum effects become inseparable. Despite the mystery, black holes have already transformed our understanding of the cosmos. Observations from X-ray telescopes, gravitational wave detectors, and radio observatories have turned these theoretical objects into central actors in cosmic evolution. The mergers of black holes, detected by LIGO in 2015, produce ripples in spacetime itself. Gravitational waves traveling across the universe, exactly as Einstein predicted a century before. Those faint vibrations carry information about their origins, allowing physicists to study gravity in its rawest form. These detections confirm that Einstein's geometry is not merely a convenient description. It is the real, measurable behavior of spacetime. The waves spread through the cosmos at the speed of light, carrying with them stories of collisions that happened billions of years ago. With each new signal, scientists test the boundaries of general relativity and find it unbroken. Still, the black hole remains a symbol of the unknown. The singularity inside is both a triumph and a warning, the place where our best theory of gravity reveals its own limits. It reminds us that knowledge itself is curved, that even the clearest equations can bend toward mystery. Perhaps one day, when a full theory of quantum gravity is found, the singularity will dissolve into something comprehensible, a region where spacetime transitions into a more fundamental structure, not an end, but a transformation. Until then, black holes stand as the ultimate testament to Einstein's vision, geometry as the language of reality, curvature as the essence of gravity. They are not merely objects, but processes, the place where matter, energy, and time fall together into the pure geometry of existence. Around them, light bends, clocks slow, and space stretches. Inside them, the universe hides its most intimate secret. Every observation, from the shadow of M87 to the ripples of merging black holes, confirms a single truth. Gravity is not a force reaching through space. It is the shape of space itself. And when that shape folds completely inward, when space-time collapses into its own depth, we see not the failure of nature, but its deepest expression. The black hole is not the end of physics. It is the mirror in which physics sees its own reflection. By the middle of the 20th century, Einstein's general relativity had reshaped our view of the universe. Space and time were no longer inert backdrops, but dynamic players in the cosmic drama. The curvature of space-time explained the motion of planets, the bending of light, and even the birth and death of stars. Yet for all its success, relativity remained incomplete. It ruled the grand scale of the cosmos, but it was silent about the microscopic world, the domain of atoms, particles, and quantum uncertainty. The deepest challenge in modern physics would be to bring these two visions together. The need for unification was not born of ambition alone. It was demanded by nature itself. Every physical phenomenon, from the glow of a star to the decay of a radioactive atom, must obey both the laws of gravity and those of quantum mechanics. But while Einstein's equations treat spacetime as smooth and continuous, quantum theory describes reality as grainy, uncertain, and probabilistic. The two pictures, though each spectacularly accurate in its own realm, refuse to fit together. Quantum mechanics emerged just as relativity was transforming physics. Its birth came from experiments that defied classical understanding. The emission of light by hot objects, the discrete lines in atomic spectra, and the behavior of electrons that seemed to move both as particles and as waves. Max Planck's discovery of the energy quantum in 1900, followed by Einstein's explanation of the photoelectric effect in 1905, marked the beginning of a revolution as profound as relativity itself. In the quantum world, energy comes in discrete packets, and the act of measurement influences the outcome. The certainty of Newtonian prediction is replaced by probabilities. An electron's position or momentum can never be known exactly. Only the likelihood of finding it in a certain region can be calculated. This indeterminacy was not a flaw, but a feature, a reflection of how nature behaves at its smallest scales. When physicists tried to apply these quantum rules to gravity, they met immediate difficulty. The mathematics of general relativity resists quantization. Unlike the electromagnetic field, which can be broken into discrete photons, spacetime cannot easily be divided into individual quanta. Its geometry is continuous by definition. When attempts are made to describe gravity using the same quantum methods that work for other forces, the calculations produce infinities that cannot be removed. Einstein himself spent the latter half of his life searching for a unified theory, a single framework that would merge all forces into one coherent whole. He refused to accept that the universe could be divided between the smooth geometry of relativity and the chaotic probability of quantum theory. To him, such a separation was intolerable. "God does not play dice with the universe," he famously said, expressing his belief that beneath quantum uncertainty lay a deeper order yet to be revealed. But nature seemed determined to prove otherwise. Quantum mechanics continued to succeed spectacularly, explaining the structure of atoms, the behavior of semiconductors, and the forces that bind nuclei together. Relativity, meanwhile, remained supreme in describing the large-scale architecture of space and time. Each theory was complete in its own domain, but incompatible with the other. The universe, it appeared, spoke two different languages. This divide became most apparent in places where gravity and quantum effects must both be strong, near singularities, inside black holes, and during the first moments of the universe itself. At such scales, spacetime would be curved to unimaginable extremes, and quantum fluctuations would dominate energy and matter. Relativity predicts infinite curvature. Quantum theory forbids it. Somewhere between them lies the true description of reality. The search for that description would define much of 20th and 21st century physics. From the equations of Einstein to the wave functions of Schrödinger, From the spacetime diagrams of Minkowski to the probabilistic clouds of Bohr, the goal remained the same: to find the bridge that connects the continuous with the discrete, the cosmic with the quantum. Yet even as the two theories resist reconciliation, their interplay continues to inspire new ideas. It was this tension between certainty and uncertainty, geometry and probability, that would lead scientists towards some of the most imaginative concepts ever proposed: the quantization of space-time, the existence of gravitons, and the possible unification of all forces in higher dimensions. But at the heart of it all remains Einstein's enduring legacy: the conviction that nature is one, that every level of reality must obey a single, coherent logic, even if our current theories only hint at its shape. The quest to unite gravity and the quantum is not merely a technical challenge. It is a philosophical one, a search for the ultimate simplicity that underlies all complexity. The next steps in this journey would lead to bold ideas: quantum gravity, string theory, and the notion that space-time itself might emerge from something deeper. The frontier was no longer about what gravity does, but what gravity is. The search for a bridge between Einstein's gravity and the quantum world began as a mathematical dream, but quickly grew into one of the greatest intellectual adventures in history. Each attempt to unite the two revealed not only the beauty of physics, but also its limits: the edges of human comprehension where geometry and probability blur into one another. At the core of this effort lies a simple question: if space-time bends and curves according to Einstein's equations, could that curvature itself be quantized, broken down into discrete units just as light is divided into photons? In other words, might the geometry of the universe come in tiny packets, indivisible grains of space and time? The earliest attempts to answer this came from those who tried to treat gravity like the other known forces. Physicists such as Paul Dirac, Richard Feynman, and others in the mid-20th century explored the idea of a particle that would carry gravitational influence, a graviton. Just as photons mediate electromagnetic interactions, gravitons would be the quantum messengers of curvature. In weak gravitational fields, the concept worked mathematically. Gravitons would be massless, travel at the speed of light, and have a spin of 2, consistent with the symmetry of general relativity. But when the calculations extended to strong fields, near singularities or at subatomic distances, the mathematics collapsed. The infinities that arose could not be renormalized, meaning they could not be tamed by known mathematical techniques. Gravity refused to be quantized in the same way as the other forces. The smoothness of spacetime itself seemed to resist being chopped into discrete pieces. Still, physicists persisted. In the latter half of the 20th century, two major frameworks began to take shape. One was loop quantum gravity, an approach that reimagined spacetime as a web of tiny, finite loops woven together into a vast network. In this view, the geometry of the universe is not continuous, but composed of minuscule quantum threads. Areas and volumes come in discrete steps, like the energy levels of an atom. Space, in this theory, has texture, not smooth but granular at the smallest scales, far below what any microscope could reveal. The other approach grew from the study of fundamental particles themselves: string theory. Instead of point-like particles, string theory proposed that all matter and forces arise from the vibrations of infinitesimal strings, each oscillating in higher dimensional space. The different modes of vibration correspond to different particles: electrons, quarks, photons, and, most significantly, a vibration that behaves exactly like a graviton. In this way, gravity emerges naturally, not as an add-on, but as a consequence of the theory's internal logic. Both frameworks, though elegant, face immense challenges. Loop quantum gravity provides a compelling picture of spacetime's quantum structure, but struggles to incorporate the other forces of nature. String theory, meanwhile, unites all forces beautifully, but demands extra dimensions. far beyond the familiar 3 of space and 1 of time, and has yet to make direct predictions that can be tested experimentally. Each is a map drawn toward a horizon still shrouded in mist. Despite the absence of final answers, hints of progress have emerged from unexpected places. Black holes, once thought to be pure endpoints of collapse, have become laboratories for testing the union of gravity and quantum mechanics. The study of their thermodynamics, the relationship between surface, area, entropy, and radiation, has revealed deep links between information, energy, and geometry. In the 1970s, Jacob Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon, not its volume. This suggested that the information describing everything that falls into a black hole might be encoded on its surface, a principle later known as holography. Decades later, theoretical physicists would expand this idea into what is now called the holographic principle, the notion that all the information contained within a volume of space can be represented on its boundary, just as a 3-dimensional object can be encoded on a 2-dimensional hologram. This insight, first emerging from the study of black holes, now shapes modern attempts to unify gravity and quantum mechanics. It implies that space-time itself may be an emergent phenomenon arising from quantum information, that geometry, curvature, and perhaps even gravity are not fundamental, but the result of deeper, microscopic processes. Experiments are now beginning to probe these frontiers. Observatories detect gravitational waves from distant mergers, revealing how space-time behaves under the most extreme conditions. Particle colliders explore the energies where new physics might appear. Quantum sensors measure tiny variations in gravity at microscopic scales. Each result, each hint, is another piece of the puzzle. Einstein had once imagined that the universe was written in the language of geometry. Quantum theory added the grammar of uncertainty. The unification of the two, if it ever comes, will be the dictionary of reality itself, a way to translate between the curvature of space-time and the probabilities of quantum states. Though the quest remains unfinished, it is far from futile. Every attempt to reconcile the two worlds teaches us something about the boundaries of knowledge. It reminds us that science advances not only through answers, but through better questions. The journey from Einstein's equations to quantum gravity is not a straight line, but a spiral, circling closer and closer to a truth that may reveal that space and time, as we know them, are not the foundation of the universe, but its most elegant illusion. In the decades since Einstein's death, the effort to unite gravity and the quantum has become the central challenge of theoretical physics. Each new generation has approached it from a different angle, and each has found the same haunting truth. Relativity and quantum mechanics are both right, yet they cannot coexist in their current form. The universe seems to demand a language broader than either one alone, a grammar in which space-time and probability are written as aspects of the same underlying reality. The clues come from the places where the two theories meet most violently. At the heart of a black hole, space-time is crushed to a singularity, but quantum theory insists that no information can be destroyed. When matter falls past the event horizon, what happens to its quantum state? Is it erased, defying one of the most sacred laws of physics, or somehow preserved in a way we do not yet understand? This information paradox has driven some of the deepest thinking in modern science. Stephen Hawking's discovery that black holes emit radiation, faint, thermal, and real, added a crucial piece to the puzzle. If black holes can evaporate over unimaginable timescales, what happens to the information about everything they consumed? The answer, many now believe, lies in quantum entanglement, the mysterious link that allows two particles to share a single state, even when separated by vast distances. Entanglement might be the thread that weaves space-time together, the invisible network from which geometry itself arises. In recent years, studies in quantum information have begun to reveal that the structure of space-time may indeed emerge from patterns of entanglement. In this view, space is not fundamental, but constructed from relationships, the correlations between quantum systems. The tighter the entanglement, the closer two regions of space appear. Where entanglement breaks, space itself could tear. This idea, though abstract, fits perfectly with Einstein's vision of a relational universe, where geometry is not a static backdrop, but a reflection of how matter and energy interact. The most striking realization is that general relativity and quantum mechanics may be two faces of the same coin. The smooth curvature of spacetime that Einstein described could be the large-scale average of countless quantum interactions. Just as a fluid appears continuous, though it is made of molecules, spacetime may appear smooth while being built from discrete quantum events at unimaginably small scales. The frontier of this search is now explored through advanced mathematics, computer simulations, and experiments that test gravity in the quantum regime. Physicists are learning to manipulate superpositions of atoms in gravitational fields, attempting to see whether mass itself can exist in a quantum state. Others study gravitational waves, using their interference patterns to probe the smallest perturbations in space-time. Each test brings us closer to glimpsing where relativity and the quantum world merge. Despite the mystery, one thing is clear: Einstein's insight remains the guiding thread. His insistence that the laws of nature must be universal, that every phenomenon is governed by a single harmony, continues to shape the search for a quantum theory of gravity. Even theories that depart from his equations still orbit the same idea, that reality is one continuous system, not a patchwork of separate laws. And so the story of gravity is not finished. It has evolved from Newton's invisible pull to Einstein's curved spacetime, and now to the brink of a new synthesis, where geometry and information become one. Each step has brought us closer to seeing the universe not as a machine, but as a network of relationships, between mass and energy, between space and time, between order and uncertainty. Perhaps one day, when the equations of quantum gravity are finally written, we will see that space-time itself is an emergent illusion, that what we call gravity is a reflection of deeper quantum connections woven through the cosmos. Or perhaps we will find something stranger still, a principle that makes both relativity and quantum theory special cases of a broader truth. Until then, gravity remains the bridge we have yet to cross completely, the place where our understanding bends, where the language of the large and the small meet but do not yet merge. The search continues not just in equations and experiments, but in the human desire to know whether the universe is ultimately simple, and if so, what that simplicity looks like when written in the language of everything. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. The quest to unify gravity and the quantum is the modern echo of that wonder. It is not merely the pursuit of knowledge, but the continuation of a story that began with a falling apple. A story that still asks the same question, more deeply than ever. What is gravity, if not the shape of reality itself? In the winter of 1916, not long after completing his general theory of relativity, Albert Einstein made a prediction so subtle that even he doubted it would ever be observed. If space-time could bend, twist, and stretch, then it should also be able to ripple. These ripples, he realized, would spread outward from any violent cosmic event, from the explosion of stars, from the orbit of massive bodies, from the collision of dense remnants of matter. They would be gravitational waves, disturbances moving through space-time itself at the speed of light. To Einstein, the idea was a natural consequence of his field equations. Just as shaking a charged particle produces electromagnetic waves, moving masses should generate gravitational ones. But the effect would be unimaginably small. Even a pair of stars orbiting each other would cause space-time to stretch and compress by less than the width of an atomic nucleus across vast distances. Einstein himself concluded that such waves would forever remain beyond the reach of human instruments. For decades, his prediction remained a quiet detail in the background of relativity. beautiful, inevitable, and untested. Yet, as the 20th century advanced, technology grew sensitive enough to chase those vanishingly faint signals. The first indirect evidence appeared in 1974, when astronomers Russell Hulse and Joseph Taylor discovered a binary system of two neutron stars orbiting one another. Over years of observation, they noticed the orbit was slowly shrinking, precisely as Einstein's equations predicted it should if the system were losing energy through gravitational waves. The match between theory and measurement was exact. The two physicists were awarded the Nobel Prize, and the universe had offered its first whisper of gravitational ripples. Still, that was inference, not detection. To truly hear spacetime ring, humanity would need instruments capable of measuring changes smaller than 1,000th the diameter of a proton, a precision so extreme it bordered on the impossible. Yet the challenge only deepened the determination of the scientists who pursued it. In the late 20th century, a global effort began. At two distant sites in the United States, one in Louisiana and another in Washington state, vast detectors were constructed. Each consisted of two long tunnels arranged in an L shape, each 4 kilometers in length, through which laser beams bounced back and forth between mirrors suspended in near-perfect vacuum. The principle was simple but profound. If a gravitational wave passed through the Earth, it would slightly stretch one arm of the detector while compressing the other, causing the beams of light to fall out of perfect alignment. The resulting interference would reveal the passing wave. The instrument was named the Laser Interferometer Gravitational Wave Observatory, LIGO. For years, LIGO waited in silence. The technology had to reach an exquisite balance of precision and stability. The vibrations of passing trucks, the rustle of wind, even the faint rumble of distant oceans could overwhelm the delicate signals. But by the 21st century, advances in optics, vacuum engineering, and data analysis brought the dream within reach. The upgraded observatory, sensitive enough to detect distortions in spacetime smaller than 1 part in 10 to the power of 21, began its first true listening campaign in 2015. Then, on September 14th of that year, the universe spoke. The signal arrived almost simultaneously at both detectors, a faint oscillation lasting just 0.2 of a second. When the data were analyzed, the pattern was unmistakable. A rising tone, a chirp, caused by two black holes spiraling together and merging more than 1 billion light-years away. The frequency and amplitude match precisely the predictions of Einstein's equations. For the first time, humanity had not just seen the universe, it had heard it. The discovery was announced in February 2016. It marked the first direct detection of gravitational waves, a confirmation that spacetime is not merely a passive fabric, but an active, dynamic medium. The waves carried energy across cosmic distances, arriving exactly as Einstein had foreseen a century earlier. The observation opened a new era of astronomy, one in which the universe could be studied not through light, but through the vibrations of its geometry. The implications were immense. Gravitational waves carry information untouched by matter, passing through gas, dust, and entire galaxies without distortion. They allow scientists to peer into regions forever hidden from telescopes, the hearts of colliding black holes, the births of neutron stars, the aftermath of the Big Bang itself. Each detection is a new kind of sight, a direct recording of spacetime in motion. When the Nobel Prize was awarded to the leaders of LIGO in 2017, it was not merely a recognition of technological triumph, but the culmination of Einstein's century-long vision. The faint ripples he once thought undetectable had become a symphony of cosmic truth. The discovery confirmed something deeper than the existence of waves. It proved that Einstein's theory, written on paper in 1915, still ruled the most extreme corners of the cosmos with unfailing precision. The universe itself had become the instrument that played his equations into sound. The first detection of gravitational waves was not just a scientific milestone. It was the birth of a new sense, an expansion of how humanity perceives the cosmos. For the first time, we were not observing the universe as light reflected from distant surfaces, but feeling its rhythm directly, as space-time itself pulsed across us. That faint chirp, lasting less than a heartbeat, carried within it the final seconds of two black holes spiraling into one another, a dance that had begun more than 1 billion years ago, before life on Earth had even emerged. The precision of the signal was astonishing. The black holes, each about 30 times the mass of the Sun, had orbited each other hundreds of times per second before merging. In their final moments, they released an energy equivalent to several solar masses converted entirely into gravitational waves. For a brief instant, their power output exceeded that of all the stars in the observable universe combined. Yet by the time the waves reached Earth, their effect stretched and compressed space-time by less than 1 part in 10 to the power of 21. The fact that such a minute tremor could be measured was a triumph of human ingenuity and the predictive power of Einstein's equations. Following that first detection, the floodgates opened. LIGO, soon joined by its European counterpart Virgo, began capturing more events: mergers of black holes, collisions of neutron stars, and combinations of the two. Each wave pattern told a story written in the fabric of space-time itself. The duration, frequency, and amplitude of the signals revealed the masses, distances, and spins of the objects involved. Gravitational wave astronomy had arrived. Among the most spectacular detections came in August 2017, when LIGO and Virgo observed a signal lasting more than 100 seconds, far longer than the brief chirps of black hole mergers. This one came from two neutron stars spiraling together. Within seconds of the detection, telescopes around the world turned to the same patch of sky. They observed a bright, fading glow in visible and infrared light, the first time in history that an event had been seen, both through gravitational waves and electromagnetic radiation. That single observation unified the heavens. It confirmed that heavy elements such as gold and platinum are forged in the violent fusion of neutron stars, scattered across the universe in bursts of energy that enrich the matter from which planets and life are eventually formed. It also verified that gravitational waves travel at the speed of light, exactly as Einstein had predicted a century earlier. The harmony between theory and observation was perfect. The ripples in space-time that Einstein had once thought too faint to measure were now a tool for mapping the invisible universe. They revealed populations of black holes we never knew existed, and confirmed that such objects merge frequently across cosmic history. They allowed physicists to test relativity in the strongest possible gravitational fields, probing whether space and time behaved exactly as the equations demanded. And so far, they do. Beyond the astrophysical discoveries, these waves also carry philosophical weight. For centuries, light had been our only messenger from the cosmos. Everything we knew about stars, galaxies, and the universe's evolution came from electromagnetic radiation. But light is limited. It can be blocked, absorbed, or scattered. Gravitational waves, by contrast, pass effortlessly through everything. They are direct communications from the heart of violent cosmic events, from places where light can never escape, the interiors of merging black holes and collapsing stars. To listen to gravitational waves is to hear the universe without intermediaries. It is to sense space-time itself vibrating, to measure motion not through observation but through participation. When a gravitational wave passes through Earth, every atom, every person, every molecule moves in unison with the stretching and compression of space. We are, for that brief moment, part of the event that occurred billions of years ago. The instruments that detect these waves, massive, delicate machines like LIGO, Virgo, and the future space-based observatory, LISA, are more than experiments. They are extensions of perception, mechanical sensors tuned to the deepest frequencies of nature. They allow us to hear what no eye can see, the echoes of creation itself. Each new detection reaffirms Einstein's vision. His field equations, written in the language of geometry, continue to describe a universe that moves, flexes, and sings in ways his imagination alone could foresee. Gravitational waves are not distortions imposed on space. They are space, breathing and resonating as energy flows through it. As technology advances, humanity stands at the threshold of a new kind of astronomy. Soon, space-based detectors will open the lower frequency band, capturing waves from supermassive black holes colliding in the hearts of galaxies, and perhaps from the early universe itself. These future instruments, floating silently in orbit, will let us listen to the murmurs of creation, the faint ripples left over from the birth of spacetime. The detection of gravitational waves confirmed more than a prediction. It completed a circle that began with a thought in Einstein's mind: that gravity is geometry, and that geometry can move. 100 years later, that motion was heard across the cosmos, a whisper of curved spacetime carrying the proof of its own existence. The confirmation of gravitational waves did not end the story of Einstein's theory, it deepened it. Each new detection became not just a proof of his equations, but a window into the living structure of the cosmos. Through those faint ripples, space-time itself had become a form of evidence, a record of cosmic history written in vibration and curve. As detectors around the world improved their sensitivity, the universe began to reveal its rhythm. Black hole mergers once thought to be rare turned out to be common, echoing through space with quiet regularity. Neutron stars collided in distant galaxies, their gravitational symphonies blending into the background of space-time. Scientists began to speak of a cosmic gravitational wave background, a continuous hum of merging masses from every corner of the universe. It was the universe's faint music, filling every direction, always present, waiting to be measured. Each event refined our understanding of Einstein's theory. No deviation, however small, has yet been found. The speed, polarization, and energy of gravitational waves all match the precise predictions of general relativity. Even at the limits of measurement, where gravity is strongest and space-time itself folds into extreme curvature, Einstein's equations remain flawless. A century after their birth, they continue to describe the universe with absolute precision. But their perfection also hints at mystery. The more we confirm relativity, the more we recognize its boundaries. The theory says nothing about the quantum fabric beneath space-time, nor can it explain the invisible forces shaping cosmic evolution, the dark matter that holds galaxies together, or the dark energy driving them apart. Gravitational waves can test relativity to its limits, but beyond those limits lies the unknown. Still, the discoveries continue. In 2019, scientists captured the first image of a black hole's shadow at the center of the galaxy M87, a glowing ring of light bent by gravity into a perfect circle. The image matched the predictions of general relativity with astonishing precision. The same equations that described planetary orbits now explained the behavior of light near an event horizon 55 million light-years away. From the orbit of Mercury to the edge of a black hole, the same geometry ruled all. It is a rare moment in science when theory and observation achieve such harmony. Einstein's vision, once doubted, now frames every frontier of astrophysics. Gravitational lensing reveals the invisible mass of galaxies. Time dilation guides the precision of GPS satellites. Gravitational waves trace the heartbeat of the cosmos. The mathematics of curvature has become the foundation of modern reality. Yet, for all its triumphs, relativity does not speak the final word. It leaves open the questions that define physics today. What is space-time made of? Why does gravity emerge from geometry? How does it coexist with the quantum world? These questions are not failures of the theory, but signs of its success. It has led us to the very edge of knowledge, where the next great leap must begin. In the glow of that understanding, it is easy to forget how improbable this journey has been. The concept that gravity is not a force but the shape of space began as a thought in a quiet mind. It traveled from paper to telescope, from the curvature of starlight to the ripples of spacetime, until the universe itself became its laboratory. Every experiment, every observation, every vibration in the detectors of Earth affirms the same truth. Geometry is alive. Today, when a gravitational wave passes through us, our planet, our bodies, and the atoms within them all move in harmony with the rhythm of the cosmos. We do not feel it, but we are part of it. The space between every heartbeat stretches and compresses with the same invisible breath that ripples through galaxies. In listening to those waves, humanity has not merely confirmed Einstein's equations, it has learned to hear the voice of spacetime itself. The discovery of gravitational waves closed the last major gap in general relativity's predictions. But as with every chapter in science, the end of one certainty becomes the beginning of another question. If the universe can vibrate, can it also evolve in ways we have not yet imagined? If space-time can carry sound, might it also store memory, the faint imprints of its own creation? Those questions point toward the next frontier, where gravity meets cosmology, and where the vast structure of the universe challenges even Einstein's vision. The future of gravity lies not in disproving relativity, but in discovering what lies beyond it. The physics that explains the dark, expanding fabric that surrounds us. The ripples of spacetime have shown us that gravity is dynamic, flexible, and alive. The next step is to understand what breathes through that fabric, what force drives its expansion, and what hidden structure shapes the universe from within. The story of gravity does not end with Einstein. His general theory of relativity, though unmatched in its beauty and precision, is not the final chapter of the cosmos, but a doorway to something deeper. It explains how space-time bends, how light curves, and how time itself slows. Yet it leaves unanswered why space-time exists and what shapes its hidden structure. Beyond Einstein's horizon lies the unfinished story of gravity, one written not in forces or fields, but in the still unrevealed language of reality itself. In the 20th century, relativity transformed our view of the universe. It taught us that space and time are one, that mass and energy shape geometry, and that gravity is the motion of matter along those curves. Every experiment, from planetary orbits to gravitational waves, has confirmed it with astonishing precision. Yet even as the evidence deepens, new mysteries emerge, mysteries that seem to whisper that relativity, though true, is incomplete. The first of these mysteries is dark matter, an unseen presence that outweighs all visible stars and galaxies combined. Its gravity shapes the universe, bending light and binding galaxies together, yet it emits no glow, no signal, no hint of what it is. Decades of experiments have sought the particles that might make it up, but none have been found. Perhaps, some now suspect, dark matter is not matter at all, but a clue that gravity behaves differently at vast scales, that Einstein's equations, though perfect near stars and planets, may require modification when stretched across cosmic distances. The second mystery is even more profound: dark energy, the invisible pressure that drives the universe's expansion ever faster. It is not merely pushing galaxies apart, it is altering the destiny of the cosmos. In Einstein's mathematics lies a term, the cosmological constant, that could represent this effect, an energy intrinsic to empty space. But the value required to explain the observed acceleration is infinitesimally small compared to what quantum theory predicts. The mismatch between the two is so vast that it stands as one of the deepest puzzles in modern science, a sign perhaps that we still do not understand the true nature of space itself. At the smallest scales, another frontier emerges. Quantum mechanics, which governs the subatomic world, and general relativity, which governs the cosmic, are both true, yet they speak incompatible languages. Relativity describes a smooth, continuous space-time. Quantum theory demands a jittery, discrete one. When the two collide, in the heart of a black hole or the first instant after the Big Bang, their equations dissolve into infinities. The very fabric of reality seems to unravel. The search for a unified theory, one that merges Einstein's geometry with quantum mechanics, has become the great quest of modern physics. Some believe that string theory may provide the answer, describing all particles and forces as vibrations of tiny strings existing in higher dimensions. Others pursue loop quantum gravity, in which space itself is woven from microscopic loops, giving geometry a quantum grain. And still others suspect that space-time is not fundamental at all, but emergent, a pattern born from the entanglement of quantum information, as though reality itself is a hologram projected from a deeper, unseen order. Each idea is bold and none yet proven, but they share a common spirit, the belief that gravity, quantum theory, and information are not separate chapters of nature's book, but different pages of the same story. Einstein's curved space-time may not be the foundation of reality, but a magnificent approximation, the surface of something even more intricate and profound. Meanwhile, the instruments of observation reach ever farther. Gravitational wave detectors now listen to the vibrations of colliding black holes, their ripples confirming relativity in the most extreme conditions. The Event Horizon Telescope peers into the hearts of galaxies, capturing the shadowed rings of light that bend around spacetime's edges. Soon, space-based detectors will open an even deeper channel, listening for waves from the first seconds of cosmic time, perhaps echoes of the universe's birth. Each new discovery sharpens the paradox. Einstein's equations continue to work perfectly, even as they point toward mysteries they cannot explain. It is as though the universe is speaking through him still, telling us, this is true, but not yet complete. And so, the future of gravity lies not in overthrowing Einstein, but in transcending him, in finding the deeper framework from which his vision arises. That next theory may not speak of curvature and force, but of information and connection. It may show that space-time itself is not a stage, but a consequence, that the geometry we inhabit is the visible shadow of a hidden architecture as yet unseen. When that understanding comes, whether in a decade or a century, it will not erase Newton's force or Einstein's space-time. It will include them, as both men once included the ideas that came before. The truth of the universe has never been replaced, only refined. Gravity will remain what it has always been, the expression of structure, the quiet order beneath motion, the invisible harmony between matter and meaning. Perhaps the final revelation will show that the universe is not held together by a force, but by relationship, that every atom, every star, every moment is bound by the geometry it shares with everything else. For now, we stand where Einstein once stood, on the edge of understanding, looking into the unknown. The equations that once bent starlight and predicted black holes have carried us to the threshold of something even greater. The next step will not only explain gravity, it will explain existence itself. And when that day comes, the cosmos will speak again, not in words or waves, but in the silent language of geometry, in the quiet curvature of reality. It will remind us, as it reminded Newton and Einstein before, that the universe is not ruled by forces reaching through space. It is space. It is time. It is the shape of everything, the thought of gravity written in the fabric of reality.